Hello. So, welcome to the stream today. Let's see who's on stream. Hi. So, today we're going to solve some problems on coloring and dominoes. Oh, hi Pradyum. So, we're going to solve a few problems on coloring and dominoes. Well, not just dominoes really. Dominoes are essentially 2x1 strips. Okay. So, such 2x1 strips are called dominoes, but it could be triminos, I guess. I mean, if there are three, there could be 3x1 strip, 4x1 strip. More generally, n×1 strips you could have. And you could have some coloring problems. Some mix of these various kinds of problems is what we're going to look at. Okay. All right. So, let's get to this. So, I'm planning for this to be a short session. Let's see. I'm going to teach you a bunch of tricks today. Let's get started. So, let me start with the classic problem. If you have never seen this before, I want to start with a classic problem, very well known. So, here is the classic puzzle. Okay, the most basic one. You have an 8x8 chessboard, and in that the northeast and the southwest corner, okay, unit squares have been removed. This is being given to you. Question is it possible to partition such a board into 31 dominoes? Can you cover it? So, essentially, if you have a square like this, the 8x, instead of 8x8, let me draw a 4x1 4 for you. Okay, and what has happened is that this piece and this piece has been removed. Okay, these two pieces have been removed. Now, if they have been removed, let's erase them. Okay, these have been removed. It's a very classic problem, actually, puzzle. It's more of a, generally also considered as a puzzle rather than a math problem. Okay, so, but I think all math problems are fun puzzles anyway. So let's see. So supposing you have something like this. Okay. Can you fill this by, oh, hi, Abhi, Harishan, welcome. So, can you fill this entire board by 2x1 dominoes? That's the question. It's very classic. I think many of you might have already seen it. So, the way to think about this problem is that look at the question. The question, the way I've drawn in this problem, if you notice, the colors on the chessboard is not important. Whatever be the color, one can always ask this question whether you can fill these by, can you tile rather this entire board by these 2x1 dominoes. Meaning, can you place one, you could place like this, one like this, one like this, one like this, and you can try. But if you place it like this, then you'll see you'll be in trouble. Looks like if you try, you can't. Okay. If you start filling it in, see, at the end you could not do it. So the question is, can you argue somehow you can never do it? Okay. So it turns out yes, you can. And the way to do this, so we are going to see a trick that we will repeatedly use. Okay. So one of my students, Lauren, had come up with this idea. We'll come to that problem also later. But one technique is, in some sense, to color the board. Okay, using black and white. Okay, so essentially, here is the coloring which I have already copied for you. What you do is you write on the board 1 2 1 2 1 2 1 2 so on. Okay, the way it's written. Now, if you notice that, you will see that out of 64, there are 62 squares, on which there are totally 62 squares. The 1 2 is like color, basically black and white. And there are, the number of ones are essentially 30. So essentially, out of 64, there should have been 32 1 and 32 2s, but 2 2s have been removed. Right, a 2 here and a 2 here have been removed essentially. So there are 30 2s and 32 1s. Okay, correct. Yeah. Oh, hi. Hi, Nabanu. So the question is it possible to partition such a board with 31 dominoes? The main point is that if you try to place a domino, no matter how you place a domino wherever, it will always cover one and another 2. Okay. Notice that it will always cover a 1 and a 2. No matter how you do it, it will cover a 1 and a 2. Which means that if you could cover this entire board by dominoes, there must have been equal number of 1s and equal number of 2s. But we know that there are 32s and 32 1s. Therefore, it's impossible to partition the board into 31 dominoes. Okay, so that is the argument. So the argument here, I mean, this is a very basic puzzle, as I've said, but I want to set the technique with this puzzle. Okay, the main thing to do, typically people use colors, but I want to insist on using 1 and 2. All right, numbers. All right. The reason is that when you start using 1 cross 3 triminos or whatever, 1 cross 3 strips or 1 cross 4, a 1 cross 2 strip is essentially a domino. But what if you have a 1 cross n strip, right? I mean, you want to generalize this trick. So we'll see more problems of this type. Okay. So the basic technique is coloring the board. I'll call this coloring the board, just writing the, somehow labeling the numbers on the board, and then checking that any strip when it sits, it will always cover, you count what and all, which different labels it covers, and then you do something with it. Okay, hi Lauren. So we'll come to, by the way, Lauren is here, and we'll come to the problem that Lauren solved using complex numbers in a few minutes from now. I also want to point out that 1, 2 can also be thought of as roots of unity if you raise it to the power 1. That is, you could have thought of this as 1 and minus 1 if you wanted. Okay. Which are nothing but square roots of unity. Okay. All right, let's move on to a more interesting problem. Maybe all of you have seen that problem. Here is a sort of a similar problem, and I want you guys to, all the people in the stream, to think about it for a minute before I start solving it. So a frog is jumping on an 8 cross 8 chessboard. Okay, so it's something similar. So let's copy this picture. Okay, frog is jumping on an 8 cross 8 chessboard, but this time this is there. At each step, the frog jumps from 1 unit square to one of the adjacent squares. Is it possible for the frog to start from the lower left corner of the chessboard and visit each unit square exactly once and finish its trip on the upper right corner of the chessboard? Justify your answer. Okay, so the question is it possible for the frog to start here and end up here, but at every move it can move to one of the adjacent squares, but it can never revisit the square it has gone. It has to visit each unit square exactly once, which means it should visit it at least once, but it should not visit it again, right? That's what it means, exactly once. And then it should finish its trip at the upper right corner of the chessboard. Is this possible? So we start thinking, how do we attack this problem? Okay, and so what happens here? Starts here. Okay, now it has to make jumps, so the frog will make certain jumps. Okay, this is bad, it can't come back. And do anything like this. This is bad. Should go here like this actually. It'll do, there are various ways to do it. So Abhi notes in chat that if there exists such a path, the number of moves would have to be even. Okay. So let's see why. So if you start from the lower end of the square, every time you make a jump, you jump from a 2 to a 1, right? So if you start from 2, you'll jump to a 1. Second time you will jump to a 2. So after 2 jumps you are at 2, right? After 3 jumps you are at 1. So you see that when you do odd number of jumps, you land at 1. and even number of jumps, sorry, odd number of jumps, you land at 2. Sorry, how much do you, in odd number of jumps, how do you land? So if you do 1 jump, you land at 1, and even number of jumps, you land at 2. Okay. So if you want to basically go starting from 2 to 1, 1 jump, 2 jump, 3 jump, 4 jump, 5 jump, 6 jump, 7 jump, and so on, you have to jump additional 63 squares to reach 2 here. Okay. So in other words, you know, from starting from 2, you have to jump an additional 63 squares to reach 2 here. You have to jump across 63 squares, but that's an odd number of squares, which means you land at a 1 at the end. But you know that if you start from a 2, the lower left corner is 2, the upper right corner is also 2. So that's a contradiction, right? You have to jump 63 squares, which is odd number, so you land at 1. But if you start from 2 and you have to end here, that's not 1 at the end. Visiting every square means you move 61 times. 61. Why? Why is it 61? It's an entire 64. It's not the previous problems. Nothing is removed. So basically you have to jump an additional 63 square, right? Alright. So this is again a similar problem. It's essentially that every time you make a jump, it's like you're sitting on a domino. Okay, that's what is happening. But it's a very similar problem with parity. Alright, so this is basic. Okay, now it becomes a bit of fun. So let's start. So 8 1 cross 3 rectangles and 1 cross 1 square cover a 5 cross 5 board. Prove that the 1 cross 1 square must be over the center unit square of the board. Okay, so let's understand this question. So you have two, three, yeah, okay, Pradyan, right? 1, 2, 3, 4, 5. Okay. All right. Oh, sorry. Okay. So thank you for letting me know. So we have to place 8 1 cross 3 rectangle and 1 cross 1 square. Is it even possible, first of all? 1 cross 3 rectangle. Is it even possible with keeping this in the middle? It's possible. Okay, it's possible. Okay, by keeping 1 cross 1 in the middle, it is possible actually to tile 8 1 cross 3 rectangle and 1 cross 1 square. Now we have to argue that the 1 cross 1 square has to be at the center of the unit square of the board. So I want to basically teach you guys the extension of the same trick. Notice now you have a 1 cross 3, 8 1 cross 3 rectangles, right? Earlier, to cover 1 cross 2 dominoes, we started labeling the entire board repeatedly, periodically with 2 colors, 1 and 2, or A and B. Okay. Rishan says color it as 1, 2, 3. Always one of them is extra. That is correct, Rishan. That's correct. One of them is always extra for sure. But why is that extra thing in the middle of the board? That's certainly true. You are right. Yeah, that's correct. Which one that is extra must be covered by the unit square. However, the question is, why should it be at the center? Why should it be here at 1 cross 1? Right. So I want to show you guys the technique, okay, so that you guys learn it. So here is the technique. Again, let's label it like this. That is, let's label this A, B, C or 1, 2, 3. I mean, since we called it 1, 2 earlier, let's call it 1, 2, 3. 1, 2, 3, 1, 2, 1, 2, 3, 1, 2, 3, 1, 2, 3, 1. Just continuously label it so that always, however you place a trimino, I mean, if you place a 1 cross 6 strip, one of different color will be covered, one of each color will be covered. So 3, 1, 2, 3, 1, 2, 3, 1, 2, 3. Okay. Okay. So now, if you try to see the coloring, you see that no matter how you place the 8 1 cross 3 rectangles, no matter how you place them, they will always cover one of 1, 2 or 3. That's how we have written them, right? We have written them in cyclical order. I mean, we have written them in continuous, we have tried to write them continuously, so that no matter how you place the trimino, it will always cover 1 of 1, 1 of 2 and 1 of 3. That's the strategy, right? That's how we wrote it, we colored it. Now this tells us immediately, we can count now. There are how many ones? 1, 4, 4 plus 1, 5, 5 plus 3, 8. There are 8 ones. And how many 3s are there? 1, 4 and 3. That is, there are 8 3s. And how many 2s are there? Remaining are 2s. So 5, 7, 9. So there are 9 2s. Okay. So very clearly you see that if you are covering the 1 cross 1 square, that 1 cross 1 square must be sitting on a 2. Okay. In other words, it must be covering a square labeled 2. So 1 cross 1 square covers a square labeled 2. Correct? Because 1 2 is extra essentially, right? And we know that all the triminos, the 1 cross 3 rectangles will always cover a 1, a 2 and a 3. So therefore, what remains, one extra thing that remains must be, if you take 8 units of 1 2s and 3s, there is 1 2 that remains, okay, while coloring. So therefore, the square, the 1 cross 1 square must be sitting on a 2. But that still doesn't tell us why it should be the center square, right? It's a bit of a problem. How do you solve this problem? It could be this 2, it could be this 2, it could be any one of these 2s. It could be this 2, it could be this 2. Which 2 is it? Okay, so here is a very interesting observation. Yes. So as Abhi notes in chat, there is a, okay, Abhi has a guess that try an alternate coloring. Okay, oops. Try an alternate coloring, he says. Yes, Abhi. So what is a simple guess to make sure? Look at the coloring carefully. What is a simple transformation that you could do to these colorings, okay, in such a way that the only common square having 2 is the center one? Do you have a guess? Yes. So Rishan notes, why not reflect? So let's try that. Does it work? So strategy is to reflect. Okay. So let's reflect 2, 2, 2, 2, 2 and 1, 3, 2, 1, 3, 1, 3, 2, 1, 3 and this is 2, 3, 1. Actually, you can just fill it in, right? 3, 1, 2, 3, 1, 2, 3. Sorry, I think I wrote it all wrong. I think when we reflect, we should go in opposite order. 2, 1. Sorry, did I write it correctly? When I reflect, I want to reflect. I thought reflection should work, so reflect. Or I think rotate. No, maybe I should have rotated. So it's like, I mean, basically rotate the coloring. Just take, or is it reflect? Yeah, it's reflect, I think. So 2, 3. This is 2, 3, 1, 2, 3, right? And 1, 2, 3, 1, 2. That's correct only, I think. And 2, 1, 3, 2, 1, 3, 2, 1, 3, 2. Does it work? Just a minute. I thought it worked. As usual, I make mistakes. So just a minute. I want to be sure whether it works. 1, 3. I think it works. Is it continuous now? Yes. Yeah, it is continuous. Alright, I mean, it has to be. I think when reflecting will not change the consecutiveness of the coloring. So now you see, it's amazing, right? These two things, the only thing in common is the center square, where twos are common. Yeah, it's correct. Amazing, right? So the proof is over. So this middle square must be the 1 cross 1 square. Yeah, it's really nice. Yes. Alright, so this coloring business is, again, I mean, the way I think about this 1, 2, 3 business is actually, you could write this as 1 omega, like omega square also if you want. I mean, if you want to do something with complex numbers, actually just the numbering was enough here. We didn't use any complicated arithmetic property right now. We're just using its consecutive. Each one appears once. So, of course, you can write 1, 2, 3, 1, 2. You're writing cyclically, right? 1, 2, 3, again 1 starts, 2 starts. It's like writing powers of omega. That's all I mean, like 1 omega. The reason why I use omega is simply because, notice, the same effect would have been achieved if I said something like ijth entry is omega power I plus j. If I say the ijth entry of the matrix, if I think of this as a matrix, and I look at the ijth entry, then so here's a little bit of a prelude, okay, of how that will help us understand this question and the previous questions as well. So when you look at the previous question, if you remember, it was like 1, 2, 1, 2, 1, 2 and so on. It's basically you are coloring it by 2 colors, right? So there also you could have said that the ijth entry is minus 1 power I plus j. Okay, if you put ijth and minus 1 is basically the square root of unity, right? Minus 1 square is 1. So minus 1 is the square root of unity, primitive square root of unity. So if you take aij is minus 1 power I plus j, automatically when you write the entries, minus 1 power 1 plus 1 is 1, minus 1 power, then I plus j, one of the I and j will increase by 1. So it will multiply by minus 1, then again next one will be 1, next one will be minus 1 and so on. The cyclically writing business that we are doing by hand can explicitly be stated directly as if use aij is minus 1 power I plus j. In this problem, if you wanted to, rather than color, I mean, you can color it, of course, there's nothing wrong with the coloring. We have not yet used any arithmetic property right now. So Yet the coloring has a natural thing that the cyclicalness will come simply from roots of unity. So for this problem here, the one that we are discussing here, here you could have taken this to be omega power I plus j, where omega cube is 1. Omega is the cube root of unity. This is e power I 2 pi by 3, or if you know, it does cos 2 pi by, if you don't know e and all, then it's just this one. Okay. So this is basically a cube root of unity, and cube root of unity also have the same property that, you know, as you keep adding, it will be cyclical. You'll have like omega square, omega cube, then omega square, then 1, and similarly here if you write, it will be 1 omega square, 1, and so on. Okay. So it will exactly work that way, but you have a uniform formula. It's not like by hand you are trying to come up with some cleverness, right? You just wrote it in one shot. Okay. Now where it really shines is in more complicated problems, where you just don't have a bunch of things sitting there idly and you're covering something, but you're making a move. You're making some move, and there was a Indian TST problem I uploaded on the channel last week. No, I think Tuesday, sorry, when I couldn't do the stream, and Lauren came up with a nice solution. Okay, so I think Lauren is around, okay, for this problem. So some of you have already seen his solution. So this is the Indian TST 2004 problem, where there's a game of pebbles that is played as follows. Initially there is a pebble at 0, 0. In a move, one can remove a pebble from I comma j and then place one pebble at each of I plus 1 comma j and I comma j plus 1, provided that I comma j had a pebble to begin with and the other two did not have a pebble. Okay. So wait, I didn't upload it on the channel. Rishan is asking. I thought I uploaded a problem on the channel as a community post. Yeah, I uploaded it as a community post. Prove that at any point in the game there will be a pebble at some lattice point a comma b with a plus b is less than or equal to 3. Okay. So yeah. Oh, Lauren, I didn't see it. Okay. All right. So I wanted to say that how does one come up with you know, how does one attack this problem, and is there a proper way to attack this problem? So one of the things you would like to do for this problem is come up with this kind of a labeling. Okay. So here is Lorentz solution, and the idea is exactly the same. You have 0, 0. This is not a domino problem, but the idea is similar. Okay. You can make it a domino problem if you want, essentially by putting squares here. Actually, you could have made it into a domino problem by covering it with squares like this, and then stating the problem in squares instead of lattice points. It's just a matter of technique of, you know, sometimes you say in terms of grids, sometimes you say it in terms of lattice point. I mean, sometimes you say in terms of lattice points, sometimes you say in terms of dominoes, but in terms of the squares, but you know, they are related to each other. I mean, a modern mathematician might call it the Poincaré dual version of each other. Okay, but anyway, so let's come back to this simple problem. So you have, the statement looks simple, okay, but the problem is very tricky. If you 0, 2, sorry, 2, 1, I think this is 1, 0. This is 0, 1, right, and so on. So now here is the thing. One of the standard things to try is always try these complex number assignments. Okay. Actually, a power I plus j, can you assign a power omega power I plus j to the ijth entry? Think of this as a matrix, this grid as a matrix. To the ijth entry you assign omega power I plus j as a value. So now what you can do is, if there is a pebble, there are two things that can happen. There is a pebble at a point, or there are no pebbles at that particular point, right? There's either a pebble or not at every point, basically. So what you can do is you can decide to, so here is the constraint that Lauren came up with. He said, why don't you take omega power I plus j, okay, for the ijth entry, check whether the ijth entry has a pebble or not. Okay, let's say this is the ijth entry. Okay, so this is some point I comma j. Check whether this has a pebble or not. If it has a pebble, then say that small aij is 1. If you say no pebble, then aij is 0. Okay, 1 or 0 has ij has a pebble, ij has no pebble. Okay, let me write it neatly. ij has no pebble. Okay, all right. Now he wants to count omega power I plus j. He wants to basically multiply all those places where there is a pebble, and when there is no pebble, he wants to divide by it. So in other words, he wants to basically do the following. It looks scary, but just hold on for a while. He just wants to take this. Okay, note that this looks complicated. Okay, I think there's a better way to say this. All this is saying is, if you are finding this scary, all it is saying is I plus j, if it is this is saying if aij is equal to 1, which means ij has a pebble, then this will be omega power minus I plus j. Notice that when you put aij is equal to 1, minus 1 power 1 will become minus 1. So this will become whole thing power minus 1. So it will become omega power minus I plus j. If aij is 0, then this will become 0. Minus 1 plus 0 is 1. So there will be just plus I plus j. Okay, so omega power plus I plus j. Okay. Yeah, I mean, Lauren, I think we can do it either way. It's just that the initial condition will be when I comma j, only at 0 0 there is a pebble, right, initially. So I think it's not visible, but let me just look at. So initially there is a pebble at 0 0, right. So when that means the initial at 0 0 means when you calculate here, what does it mean? So omega power 0 0, I guess that's why you are saying plus 1, so that you have at least 1 omega. Is that why you are saying plus 1? Will it affect the argument? Yeah, I guess fine. I'm wondering whether okay, let's run through the argument, and I think it will affect. Maybe it becomes it starts with a 1 and it will remain 1 is the problem. If there are no pebbles at all, also it will be 1. I think maybe that's the problem. That's what you're saying. If there are no pebbles at all, which means aij's are all 0, then you will have omega power plus I plus j, and yeah, it will be a problem, I guess. Okay, fine. So Lauren suggests that you need to put a 1, or else the invariant won't work. Okay, so let's do that. Okay. All right. So now what Lauren is saying is the following. At any point, there will be a bunch of pebbles on the board. What you do is you multiply all these omega I plus j plus all these expressions, omega I plus j plus 1 power minus 1 is I j, multiply product. Okay. I mean, and since we care about in this problem, remember we have to just prove that at any point there is a pebble at some lattice point with a plus b less than or equal to 3. Instead of having an infinite product, just so that we don't have an infinite product, just look at the product, look at this quantity s. Okay. Now, what is the point of this calculation? So the point of, I think, Lauren's calculation is the following. Why did he come up? I mean, what is the point here? Is that if you look at this expression, right, this expression actually does not change when you take a pebble out of ij and place a pebble each on I comma j plus 1 and I plus 1 comma j. So let's see why. So supposing you had a pebble at I comma j and you removed it. Removed it means to the contribution, when you calculate the sum of when you calculate this product for the new board, you will first remove the pebble. The moment you remove the pebble, the omega power I plus j plus 1 power minus 1 power aij, I mean aij was anyway 1, so power minus 1 basically got subtracted, I mean got divided. Okay, this got divided. But then you placed 1 at I comma j plus 1 and I plus 1 comma j, which means to the product those particular contributions got multiplied, right? When you multiply now I comma j plus 1 and I plus 1 comma j terms will get multiplied. So which means omega I plus j plus 2, because I plus 1 plus j plus 1 is I plus j plus 2, power minus 1 power 1, obviously because you placed a pebble there, into another expression of the same type, so square. Okay, so this is what will happen. But now you can take this square inside. Okay, so let me do the, let me not skip the algebra. S by, notice you can write this entire 2 omega square below inside. So you can write it as omega power minus 2 power I plus j plus 2 divided by omega power minus 1 I plus j plus 1. Okay. So now what happens? What is this? So you can take 1 omega square minus omega square common out, and I think, okay, I didn't do this calculation, I did it with I plus j. So let's see, you can take 1 omega power minus 2 common out, then you will have omega power minus 2 power I plus j plus 1 divided by omega power minus 1 power I plus j plus 1, which is nothing but omega minus 1 I plus j plus 1, right? Is this, no, it's not cancelling, right? What, am I making a mistake? Should have cancelled for me, cancelled earlier. Just a minute, I think I made a mistake somewhere. No, it's correct. Omega power minus 2 is just omega, no? Omega power minus 2 is just omega. What mistake did I make? I think the S should not change is the main point here, but I am not being able to check. How do we come up with this? Let's see again. It should work. I've done it earlier. Let's see, what was the omega power I plus j plus 1 power minus 1 into omega power I plus j plus 1 power minus 1 is omega power I plus j plus 2 minus 2, that's correct. It's not working for me. If I directly put I plus j, it was working though. How did it work? 0, 0. I don't think you have to put. No, I think this I plus j plus 1 business is not working. Can anyone check the calculation once? Plus 2 upper minus 2 omega I'm getting S into omega power 2 into I plus j. Rishan is saying, no, Lauren did it clearly. You are right, Rishan, but that's not a general principle. This principle works in general. I mean, it works in general, meaning there are many problems where the invariant, if you just write the matrix cyclically as omega per I plus j, it will work. I mean, I just changed it because Lawrence said I plus j plus 1 is what you have to put. Let me do it with I plus j only. It will be an invariant. We'll fix that later. So I think what I worked out with was I plus j. Okay. So in fact, I plus j, it will produce the invariant correctly. But will it be helpful or not? I don't know. That Lauren is saying it won't. That we'll see later. If you put I plus j, and I didn't put that extra one that he told, okay, I think it will work. I have tested this will work. So if you take S to be product of I plus j, it may not be helpful though. So Aij, if you multiply, okay, for all of them, then let's note that if you remove the pebble, you will essentially divide by it. Okay. But if you now place the pebble wherever it is, it will be I plus j plus 1, and of course there is no Aij. Aij is 1, we know already. So this is like minus 1, that also we know already. Okay. And here minus 1 power minus 1 power 2 you will get. So this will be S power omega power minus 2, which will be omega power minus 2 would be what? Omega power I plus j plus 1. Okay, no, I think still suffers the same difficulty. Omega power minus I plus j. I think it suffers the same difficulty still. So I must have done a calculation mistake then. S is omega, the same problem appears, 2 I plus j plus 1, which means we should be able to fix it by changing it to something. What did I do? Yeah, this doesn't work. So I think if somebody wants to see, well, if I think if somebody wants to see Lawrence solution, it's there. Apparently, he has put it up in chat in the community post, so you can look it up. I am more interested in a more general technique rather than ad hoc techniques. So in other words, like, is it possible to come up with? I think there is a way to do this here. Although I think I might have made a calculation mistake. It seemed to work earlier when I assigned something. Can you basically either it's I plus j or I minus j or something like that. Okay, so I think if you do that, I mean, maybe I don't know whether this will work. So let me try one more time. Omega power I minus j minus 1 omega power omega power minus, maybe I made a mistake. I forgot the negative sign or something. This is the kind of mistake I'll make. So this is the variation, right? If you include and even this notation, I mean, if it's scaring you, then you can just write it as Aij and change it to plus 1 minus 1. Okay, that's the same thing. It's, the main idea is just whether you're dividing and multiplying. That's the main thing I want to do. So minus I plus 1 minus 1 will cancel. Omega power minus I minus j 2I minus j omega power minus I minus j. Now it has not changed, no? No, it has not changed. This is invariant. Is this correct? So this is an invariant. I don't know if this is useful though. We have to fix it to be useful. Okay, so in case, so Nabanu is saying it's not scary in quotes. Nabanu can be made less scary for you, but it will be totally useless because you can't remove that quantity when in the exam. What is the use? So here is the point. Unless you have a general technique or a general plan of attack, all kind of beautiful looking proofs are useless if you can't come up with it. No, you can just watch them with wonder, but in the exam it's useless. So we need some kind of motivation or a technique, some kind of motivation which will help us like guess those kind of quantities. So I'm trying to say that throughout, not just these, there are more problems actually, where one assigns to the ijth entry some kind of either complex number per I plus j. This is like basically generating function kind of techniques. The ijth entry is to be like aij omega per I plus j. That is the, and you sum it up. In this case we are multiplying. Okay. So we are trying to come up with some strategy. Like for example, it need not be ij, I mean it need not be omega also. It can be like some other number. Omega is not, the omega is not playing any role actually. It can be x power I plus j. You can call it x power I plus j also. I think it wouldn't have mattered. Okay. So just that the fact that putting it omega here was useful because maybe it will simplify the calculation, right? Like you put an x there, you rearrange and you try to see which x, if you put that move, it will keep it invariant essentially, right? So for example, if it's scaring you, then you can do the following. Instead of my 1 comma 0, 1 comma 0 is like more of the pebble is there and the pebble is not there. Literally from English it will convert to math, that's why I put it. But you can also put plus 1 minus 1 if you want. It's the same thing, right? So first thing is the following. If you take the let ijth entry, so basically you just multiply omega power I minus j. So if you want to make, you can write it like the following. Let's say omega power I minus j if product over all ij that contains a pebble. Right. So now I just did the calculation. You guys can check now. Let's check it again. I think that this quantity is an invariant. Although I think this quantity is useless, so we have to modify it. Omega power I minus j. Let's say ijth entry has a pebble. Supposing you removed it, then it's as good as dividing by this ijth entry. I mean that quantity. When you remove the pebble, you have to remove it from the product. Removing it from the product is like dividing by omega power I minus j. Then you have to place pebbles at I plus 1 and j and I comma j plus 1. That is same as multiplying, I guess, the following: I plus 1 minus j and I plus j minus 1. Okay, I plus 1 minus j and I minus j minus 1. Right, this one is I plus 1 comma j. And this is I comma j plus 1, okay, entry contribution. And I am thinking it should work. That is omega power minus 1 will cancel omega power plus 1. And what will remain is omega power I minus j and another omega power I minus j. Okay. So omega power I minus j the whole square divided by omega power I minus j, it's again omega power I minus j. So what has happened is that when you did this move, the expression should have remained the same. I think it's not working, right? What should we want? We wanted to prove it's equal to 1. Okay, now we notice that x is not playing, omega is not playing any role here actually until now. Why not place it x and rearrange? Let's see. Can we make it equal for x, 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 x? No, we want this to be 1, right? I think I made the mistake of trying to make it equal to x power omega power I minus j. Okay, so now what is this quantity? How would you place this quantity? Either this one or x power I minus j is equal to 1. Won't work for all of them. Yeah, no. So I think the mistake is that, okay, so I have to now then come up with the original one. So I want a uniform answer, okay. So maybe I'll just end up discovering Lorentz answer only. So let's see, x power I plus j plus 1 square divided by x power I plus j is 1. Will that help? X power 2i plus j, 2i plus 2j plus 2 is equal to 1. Yeah, it won't work in general, that's true. So to come up with, okay, so I think Lauren has an answer. So Lauren's answer is the following. I can tell for the stream, if there are people, you can look it up in his community post. I think he has answered. But I would like to know how to come up with this assignment in more generality. Like, is there a general kind of a formal assignment that will give it? Okay. So I think he said something like assign omega to I comma j. I guess he said assign omega to I comma j if I plus j is even, and if I plus j, is this the correct one? I forget. I plus j is odd, you put omega square, I think. This is the assignment, Lauren. Omega I plus j is even, then it's omega, I plus j is odd, it's omega square, which is basically omega power minus 1. Yeah. What is that? That is the same as saying minus 1 power, it's the same, no? Oh, okay. It is omega power minus 1 power I plus j. I see. So, okay, nice. So, minus 1 power I, minus 1 power j. I see, okay. Not bad. This is still better. This is a general form for it, right? I want a general form for things. So, that's why. So, omega power minus 1 power I plus j is reasonable. So, okay. So, let's just check. So, I think Lorentz claim was if you take out this and you go up and put minus 1 power I plus j plus 1 whole square, then what happens? So, you will have omega square power minus 1 power I plus j plus 1, correct, divided by omega power minus 1 power I plus j, and this entire quantity is this extra plus 2 plus 1 can be written as into minus 1, which can be taken inside, and both are omega power. Oh, nice, absolutely nice. Okay, see, the proof is nice. Okay, plus 1. Okay, all right. So Lorentz assignment is nice. I like the fact that it has a general form. Okay, so the assignment was minus 1 power I plus. There are very few things we can do. I was trying to do with this, okay, plus or minus 1 here, whereas Lauren was doing minus 1 power, rather he was doing omega power plus or minus. Both of us are trying to do omega power plus or minus 1 or something, but I was trying to do with I plus j, which requires some cyclicity with the mod 3. Okay, however, in Lorentz thing, I think it makes sense actually. So, in retrospect, it makes sense to me, but it didn't make sense earlier. So, the point is that why do omega is not the important thing. The important thing here is that I plus 1 comma j and I plus 1 comma j and I comma j plus 1 movement seems to have something to do with parity, plus 1 minus 1. So, his I plus j should have been attached to minus 1, they should, for the parity thing. So, it makes more sense. The way I am doing it, as you go over I and j, as you vary over the whole thing, there will be some sort of cyclicity of order 3, right? This problem has some kind of a cyclicity of order 2 essentially. Alright, but anyway, so let's, now the proof works, right? The proof is over. So you just multiply S is omega. Okay, so let's finish off the proof. So here's Lorentz proof. Now I appreciate it. I plus j less than or equal to 3 and I comma j has a pebble. You write this sum, you write this product. Okay. So now, as we saw just now, here's my argument of how it works in general. Pick what happens. Okay, so let's see. So you start with S. Now let's run the thing which we didn't do earlier. Omega power minus 1 power I plus j, you divide by, that is at the ijth entry if you remove a pebble. Then you place the two pebbles at I comma j plus 1, which will give you I plus j plus 1, and at I plus 1 comma j, which will also give you the same thing. So it's square. Now you notice that a power b power c is a power bc, right? So you can take this 2 inside. So you can write this as omega square minus 1 power I plus j plus 1. Of course, you can do by cases, okay, because this I plus j is simple enough, but this idea might work in general. So that's why I'm writing it this way. So you take minus 1 power I plus j. Okay. Now you want to write, this is minus 1 power I plus j. Even if this was only minus 1 power I plus j, we would be done. So you want to make it into minus 1 power I plus j. So you remove this one and put a negative sign here. And that negative sign you can sneak inside. So therefore this becomes S into omega power minus 2 by omega whole power minus 1 power I plus j, which omega power minus 2 by omega is just omega cube or whatever, it's just 1. So just a second. We are done. Now, okay, so 2 points. So first thing, we showed that S does not change when you make the move. It's an invariant. Okay. Once you could actually get S does not move, it's an invariant. Okay. What is the plan? The plan is the following. Initially, there is only one pebble at 0, 0. So if you put in 0, 0 here in this, there is only one pebble. So this product is a single term. It's omega power minus 1 power 0 plus 0. Minus 1 power 0 plus 0 is 1. This entire quantity is 1, and omega power 1 is omega. Okay, omega power 1 is omega. So therefore, we know that for this problem, when the pebble is on, there is only one pebble at 0, 0, S is omega. So therefore, since it's an invariant, no matter what moves you make, S will remain omega, right? And the statement that S is equal to omega would mean that there must be a pebble at some lattice point within a plus b less than 3, because if there were no pebbles, then this entire product would be empty. So the product would actually be just 1. So since omega is not equal to 1, we know there must be at least one pebble. Now I want to sort of illustrate that what if they changed I plus 1 comma j and I comma j plus 1 to something else, some kind of instead of 2 thing, maybe they said 3-dimensional or something like that, like 3 things they made or something like that. I think that or they started placing pebbles at I plus 1 and I plus 2 or something like that. I think once we have written it in a general form, we can make modifications. Maybe this minus 1 can be replaced with the cube root of unity again, like omega power I plus j, something, and we can do it. Okay, this is my hunch, but I think one can modify this invariant slightly now. Now it's in a general form to solve the more general problem, although I have not thought about it. But that's why I think writing general forms is useful. Try to solve the most general problem, then many other problems can come out of it. Okay. All right. So hopefully this calculation is clear. This makes me happy. So one of the things, at least with me, is that I like watching. I loved Lorentz proof, but at the end of the day, I want to see if there is a general way I can write it, so that I can file it away in my mind that this is the kind of thing I want to do. Okay. All right. So I'm happy with this calculation. All right. So here's another one, but what's the time? 7:45. Okay. So let's try this for a while. This is a slightly different kind of a problem. Find all ways of coloring all positive integers such that every positive integer is either colored black or white, but not both, and the sum of the two numbers with distinct colors is always colored black and their product is colored white. Also determine the color of the product of two white numbers. Okay, again it's not visible. Okay, if you think about this, so let's do some trial and error and play around with that. I'm going to think of them as a number line 1, 2, 3, 4. I think this also must have some proof of that sort, some coloring, I think, although I don't know how to get it. But no, paste as image. Yes, okay. Alright, so I've just done it for the first 10, but let's color. Okay, white I can't color, so I'll color it black and red or something. So in the chat, Rishan says product condition fixes everything else. You only have freedom of choosing primes. Why? The sum of do we even have the chance to prove primes? I don't think we have the freedom to choose primes also because of the sum condition. I mean, sum of two numbers can be primes. So there's a suggestion in chat that the even numbers should go to white and odd numbers to black. That's wrong, right? No. Yeah, that's wrong because you take two distinct two distinct colors, their sum is always colored black. In Lorentz suggestion of even and odd, if you take two distinct odd numbers, they are both black, but their sum will be even, it's white. That doesn't satisfy this. No, but odd plus odd is even. Two distinct odd numbers add to even. According to the problem, it should be colored black, but according to you, it's colored white. So Pradyun says if you select 1 as white and 2 as black, fixes everything else as black. Oh, sum of two numbers with distinct colors. Correct. Okay. Correct, Lauren. Yes, sum of two numbers with distinct colors. You're right. So that means you have to pick odd. Yeah, you're right. That works. That's correct. So I think that's what Pradyun is also saying. Maybe if you select 1 as white and 2 as black, then we are done. It fixes everything else because you chose two distinct colors. This will become black. Oh no, this is a different coloring. White, black, black. Fixes everything else as black, is it? Yeah, 1 plus 3 is again black. Yeah, black. That's correct. Everything is black. But the product of two distinct, no, it's wrong, right? The product condition will fail. If you take sum of two numbers with distinct colors is always, and their product is always colored white. Product of 1 and 3 should have been white. It's not possible. Contradict each other, yes. So let's see Lorentz coloring works. White, black, white, black, white, black, and so on. It should work maybe. Sum of two distinct colors. If you pick two distinct, it will be one odd and one even. The sum will again be odd, so it will be black. And the product of two distinct colors will always be even because I mean one odd, one even he has colored. So and okay, I think I've labeled it the other way. Maybe I should have labeled black white black white. Okay, now it works. Oops, 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 oops. Correct, correct, yeah. Now it works. This works, that's fine. Or coloring everything with the same color also works. If you fix 1 as black and 2 as white, it will work. There's no 0, I think. All positive integers. So is this the only coloring? What could be the possibilities? What if 1 was black? Okay. What was 1 was white? Can 1 be white? Can 1 be white? And 2 also, 2 is black is not possible. Then the sum should be, okay, no, why not? 2 is black, and then there's a contradiction. Everything will become black and we'll be in trouble. We saw that already. So what if both are white? Why not? Actually, okay, I mean, we can keep having white. There is no contradiction, no, because the condition is only with 2 distinct colors. So first time we should get a black somewhere. So what if the first black appears at 3? White plus black is black, but white into black will be white. That is a problem. So okay, so if 1 is white and any number n is black, we are in trouble, no? See, if 1 is white and n is black, we are always in trouble, I think, right? And if this is the first time where black appears is n, up to n minus 1 it is white. Supposing this happens, we are always in trouble, because 1 comma n is, when you add up, n plus 1 will become black. White plus black is black. Sum of 2 distinct colors is black, rather 1 and n is black, but their product must be white. That's a contradiction. So you cannot have 1 white. So Abhi says 1 comma 2. Yeah, I don't think 1 can be white. If 1 is white, then everything is white. That is the only possibility. Even if there is 1 black somewhere, you are in trouble, right? So 1 has to be black, unless everything is white. Even if there is 1 black somewhere in colored number, 1 has to be black. Okay. Now the point is that in this problem there is no contradiction or anything if you keep putting everything black, which means for the first time where white appears is the main point. Now you can keep, like, let's say, in fact let's not go very far away. Let's put, if you do black white, this is over, right? This gets fixed. So let's put black black white. Yeah, 1 white, then everything will become white. That's correct. So 1 has to be black. Now if 1 is black, let's say the first white appears at 3, because if the first white appears at 2, we have already calculated. I'm guessing that if you have black white, it's over. This is what I'm guessing, right? Because you don't have a choice, right? The even odd condition will force it. 1 plus 2 will be 3 black, you'll get black, and then you'll have 2 plus 3 is also black, 5. No, we didn't argue it actually. Did we argue it? That once you have 1 is black and 2 is white, then this has to be the coloring. Maybe there are other colorings also, right? Who knows? Okay, 1 plus 2 is 3. So this is black. Then 2 into 3 must be white. 6 must be white. Maybe you have to prove by induction or something. 6 will be white. how can we argue about 4 and 5? What happens if, I think similar to 1, there should be an argument for 2 or something like that. Like if 2 is white, then 2 plus n will be, where 2 is white and n is any black, 2 plus n will be black, whereas 2 into n must be white. So what is the problem? But there's some 2n plus n plus 2, I know this is useful. It will be 3n plus 2 must be black, and 2n into n plus 2 must be white. It's not useful, I think. 2n square plus 4n must be white. I think if we iterate, is it useful? Sometimes it's useful to iterate. 3n plus 2 must be black. So n plus 2 is black, 3n plus 2 is black. So, okay, it's not still clear. Why is 4 white? What if 4 was black? What is the contradiction? So, okay, so let's do this. Before we go ahead, let's finish off this calculation. I think black, white, there might be more solutions we're missing. 3 has to be black, no problem, because sum is black. Then the only new thing we know now is white plus black, right? 2 plus 3 is black, and 2 into 3 is white. Yeah, 4, it doesn't seem like we can say what it is. But there should be a contradiction somewhere. Let's see. I think if you get like, yeah, let's see. I think we should go something to a multiple of 4 or, by the way, no, we know it. We know what is 4. You see, 4 can't be black. If 4 were black, then 4 plus 2, 6 must have been black, which is not true. So by contradiction, you know that 4 must be white. 4 is fixed. Do you guys see it? 4 plus 2 is 6. If 4 were black, black plus white must have been black, but it's not true, it's white. So therefore by contradiction we know that it can't be black, it must be white. Okay, so it does get fixed, but it's not so obvious. It's like slightly like contradiction proof. Okay, 7, 8, and I think now we should be able to fill stuff. So 4 plus 3 is 7, that is black. 4 into 2, okay, that we can't use. Maybe we can determine what is the color of product of 2 white numbers. It's given in the problem. Can we argue somehow that product of white is white or something? In this example, it's white, no? If you could do that, then it's easy. Then we can do 4 into 2 is 8, which is white. I think it is white mostly. Because if it were black, we'll be in trouble, I think. What could be the reason? 5 plus 3. No contradiction. I can't tell what is 8 right now. Yeah, all white, all black works, Pradyum. 9, 10, 5 plus 4, this is black. 5 into 2 is white. So 6 plus, okay, 8 plus 2 or 8 plus 1. See, again we can do the same thing. 1 is black, 8 is, I mean, if this was black, then, okay, if this was white, this was black, is there a contradiction? Black plus white, 8 plus 2 would have been black. That's a contradiction, so it's white. I think this leads to some kind of induction proof. In other words, I think what is happening is n plus 2. If you are at 2n, that you don't know what is its color, then 2n plus 2 would have gotten it as 2 into n plus 1 already. So we know 2 is like white. By induction hypothesis, we might know n plus 1 is black. Well, it depends, I mean, what n is, whatever is the parity of n. I think we have to do some induction proof here. to contradict 2n, like 2n, 8 and 2. If 2n were black by hypothesis and this is white, then 2n plus 2 would have been black, but that should contradict because you have 2 into n plus 1, where 2 is white and n plus 1 we already know is black. So if n plus 1 is black, then n is even. Okay, for even n, I think all multiples of 4 it's happening. Actually, here also we see we missed 4. Next we didn't know how to get 8. Everything else we could get. So only for multiples of 4 it will, I think, give you an induction proof. Yeah. I think, okay, so for now I'll assume you guys can finish it off by induction. This is because it's just a small part of the question, right? Try finishing by induction. I think it seems to work, at least in small cases. Okay, alright, so now let's come back and see if we can attack the full problem. Can you first of all determine the color of product of two white numbers? I think most likely there's a general answer, or else why will they give it? So I'm guessing that product of two white numbers is white. That's my conjecture. Can you prove it? Product of two white is white. I think by contradiction or something we should prove. What if A into B, this is white, this is white. In general, nothing to do with this first black one white. In general, I think product of white is white. What happens if it's black? What is the contradiction? Something like this we should do. Either everything is white, in which case there is nothing to prove, or one is black and everything is black, even then there is nothing to prove because there is no white numbers only, or one is anyway black otherwise. How do we argue what is the product of white numbers? Rishan is induct on 4k plus 1. Yeah, that you can do for that previous part, but how do we answer this question? I feel like if I could answer this question, or is it that after you solve the problem only you can answer the question? It's not easy to answer otherwise. Maybe that's why they gave it at the end. Let's see. I don't know. Maybe we should pause. I think this is true, but let's see. Maybe we'll prove it at the end. Okay, maybe it's the induction kind of argument. So let's go back to our old argument. We have to start with black assigned to 1. Then to 2 we analyzed what happens if I assign white. But you can assign black. You can keep assigning black and there will be no contradiction until for the first time at some n you assign white. That you guys can see, right? I mean, there is no problem. They only given conditions for sum of two distinct colors and product of two distinct colors. So if they are not distinct, there is no condition only in the problem. So let's say there is no problem in keep assigning black. At some point, let's say you assign white for the first time. Now what can you say immediately? Because these are all distinct colors, if you add 1, 2, 3, 4 and all, it will remain black, I think. N plus 1 is black, n plus 2 is black, up to n plus n minus 1, 2n minus 1 is black. But we can't again answer what is 2n. Actually, it was the same case, n is 4. N is 2 if you put here in the earlier case, where the first time it became white. 4 we could not answer. I think it will be the same trick now. Okay, let's see. I think it should not be hard. So if you, can we just go ahead somehow? 2n plus 1. So I think you can get 2n plus 1 simply because n plus 1 is black, right? Done. 2n plus 1 also you can get. Same trick as before. Oh, this was the main case. Okay. So notice that n plus 1 is black. And you can keep doing this now. 2n plus 2 is n plus 2. That's also black. Okay. So now we have to do that trick where we say something like 2n plus 2 we know is black, we know 2n plus 2 is black, but 2n plus 2 can be thought of as 2n plus 2, right? And if 2n were white, if 2n were white, if 2n were, no, there's no contradiction, is it? What was the mistake? How did we do it last time? We need to get some white actually. How do we get a white? To get a white, we have to actually 2n. Wait, 2n is actually easy, no? Why did we make a mistake last time? Oh, last time 2 into 2 we could not do. For n greater than 2, there's no issue, right? It's easier. 2 into n, black into white is white. So where is the problem here? Seems like we got all the way up to 2n. Can you just prove it in general? Like, what is the claim now? The claim is all multiples of n is white, others are all black. Is that true? Let's say you have any number capital N, okay, and if n divides capital N, the claim is that black must be assigned. It's black assigned to n, otherwise white assigned, whatever. See, I've written equivalent anyway. Can we prove this? Should we do it by division algorithm? I think anyway n is the smallest such number also. Typical division algorithm proves n is the smallest number with a property that white is assigned. Typical. So n is equal to nq plus r. Something will happen now here. R is strictly less than n, 0. So r obviously, if it's not 0, let's assume we'll prove by contradiction. Suppose r is not 0 because 0 it doesn't start from 0. Suppose n is of the form nq plus r where r is strictly positive. We'll try to prove that then capital N must be assigned black. Okay, r is already black. R is already black. This is black. We want to prove a capital N is black, so we have to prove n into q is white. So we know n is white, but we don't know what q is. We want to, if you could prove n into q is white, we are done. How do we prove this? Oh, it goes back to this. I think we have to show somehow the product of two white is white. If you show that, we are done, right? Because product of a white and a black is already white given in the condition. If you could prove product of white and white is also white, then product of white and any number is white. So then once n is white, q is any number, we don't care. N into q is white. R we know is black because r is less than n, right? All the numbers initially are black, and black plus white is white. Black and plus white is black. So we are done. So we would have proved that if n does not divide capital N, then black is assigned to n. In the other case, when n divides n, once we have proved that any number into white is white, capital N, small n divides n means capital N is a multiple of n, and n is white. So therefore we are done. The product must be white. So I think we really have to prove product of two white is white somehow. Reduces down to proving product of two white is white. The problem is solved. Right? So how do we prove product of white is white? This looks like ideal condition, ideals. What is the product of white is white? If you how does one prove this? Product of white and black, A is how do we do this? Supposing A is black, A is white and B is white. How do you prove A into B is white? In general, we have to prove for such an assignment. Is it obvious here in this assignment actually? The product of white is white? No. No, in fact, that's what we had to prove. We don't know this assignment, so we have to prove it in general without knowing what the assignment is, because we need to use it in the argument. Rishan is saying use AB is A plus, okay, use AB is A plus B minus 1 into A. It is equal to 2A plus B minus 2 into A and so on. So A and B are white, okay. Now, okay, I'm using B for, let's use some L and M, okay, sorry. So I'm already using B for black, it's very confusing. To use it as a variable and a color assignment also. So let's call it some L and M. I have not used L and M, okay. So L and M are white, then LM, Rishan is saying, notice it's L plus M minus 1 into L. How does this help? So LM, suppose they were black, suppose it was not white, supposing it was black, and L is anyway known to be white, then if this is it, there's no contradiction. White plus white can be anything. We want to prove it's white though. To prove if, yeah, I don't know how it's helping. M minus 1, I see, M minus 1 is black, no, M minus 1 we don't know what it is. L is white, white into, if M minus 1 is black, maybe you have to do cases. So what is, I don't see Rishan's suggestion, what to do with it. Maybe you mean pick a, write it like this and do some minimality argument, I think. Do something like find the first k where k into L where it fails or something. So suppose, yeah, that kind of argument we can run, right, typically. So you say something like, suppose we want to prove product of two whites is white, okay. We can try to find the first place where it fails for L or something like that, like the smallest possible numbers, product of numbers or sum of numbers, some condition we have to put so that this condition fails, that the product of whites is white. Which are the smallest two numbers, or which two numbers have the smallest product with that property or something like that. Where pick those two L&M, because right now it's random. So suppose L white and product is black, product is assigned black color, and L into M is the smallest such number, okay. Now pick a k less than M that is white. Suppose there is a k less than M that is white, that's one case. There's at least one k less than M that is white. Then this into this will be white, this is white, and this also is smaller, so this is white. There's no contradiction again, white plus white you will get. White plus white can be black. I don't know. How do you deal with this? Y is product of whites white, but I think this is a nice trick actually. This is a nice technique. The answer is somewhere here, although I don't know how to do it. Very close. We are very close. Product is white is what we have to prove. You could prove one of them is black. You can always find one of them black, one of them white. We are done. No, no, we can't. We'll have to prove by contradiction. Here, how did we prove? The only case we have proved is this one, right? So, to go back to it, how did we prove things like product of white is white? 6 into 10, 60 is white. How will you prove 6 into 10 here, for instance? How will we conclude 60 is white actually in this argument? Yes, 60 can be written as sum of two odd numbers or something, and smaller odd numbers, and that we would have proved by induction. Maybe we should do an induction on LM. Can we argue? Oh, but we don't know which ones are assigned white. Yeah, I think we should do some kind of induction. So we do the following set. So let S be the set of integers colored white. Set of integers colored white. Let's say that's not enough. We need to put more things. Product of I think we should run some induction. Let's say we have already proved product of white is white up for all numbers. Okay, how do we put the induction sum? Is it on L plus M? We induct on L plus M or something. Some strong induction we have to do. So for all values of L plus M less than a given quantity K we have already proven, let's say. Now L plus M is equal to K, and L is white and M is white, and now we have to prove the product LM is white. So then can we do what you are saying? LM KL plus M minus KL, and we write it as sum of these two. Individually L plus K and M minus K plus L will be less than K. Okay. So therefore L is white. Okay, I think the stronger thing to claim obviously is that even if one of them is white, for all L plus M less than K, we have proved that if one of them is white and both the numbers are L and M are, I mean the sum satisfies this condition and one of them is white, the product is white. Obviously because the other case is trivially true, right? It's given, trivially meaning directly given in the problem. One of them is black, the other is white, product is white. So which means if one of them is white, we are done, right? So, but still it's not useful because this is white and this is white. It's not useful. How do you prove LM must be white? I think the only way to prove it is by not working with LM actually. We should add something to LM. This is not a good strategy, I think. But decomposing is not telling us anything. This is white plus white, and in the worst case we make it white and black, it will tell it's black. It's not helping. I think LM plus something should be something we should for sure is white. Something like that we should do. Then we can do contradiction. Supposing this is black, that is white, it will force it to be black or something like that. Right. So I think we should go ahead. So it should be like something like L plus K into M. Like this it should be. So it should be like, for some reason we know this is already white. Maybe this one is black and the other is white for that reason. And we know that this is black for some reason. You know, this is black, we know this is black, or we know this is white. So I mean, the contradiction proof will be like something like this was black, this was white. Okay, so the only way we'll get a contradiction is we somehow know this is white and this is white. And if this were black, it would be a contradiction, so forcing LM to be white. That's how the proof should go. Okay, so let's reverse calculate now. So MK must be white and L plus K into M must be white. We can try to induct on that M less than something. This should finish off the proof, right? So M into K, how do we come up with this? So the product is white. Okay, it's given L and M are white. L is white, M is white, right? It's given. So we already know this is white. So we should make this black. Then the product will become white, right? We should make this black and we should make this also black. Then we are done. Okay, so can we do that? Can we choose a case that K is black and L plus K is black? Yes, we can, right? If as long as there's one black color, we are done. We are done, I think the proof is over, right? So because if you choose, already L is known to be white. If there's one black color somewhere, that L plus K is black, L is white, sum is black. But this is black, this is white, so product is white. This is white. Now, if this was black, it's a contradiction. So therefore, LM is white. I think we are done. Okay, so let me just write the argument. There's no induction, nothing. Okay, all right. Oops. I think it's nice. Okay, all right, so let me explain and you guys can tell me if the argument makes sense or not. All right, so claim. If L comma M are both white, then L into M is white. Okay. Okay, proof. If all natural numbers are colored white, the claim is trivially true. The claim is trivially true because everything is colored white, so the product is also colored white. Suppose not, suppose all of them are not, suppose not, then some natural K is black. K is black. Some natural K is black. Now, clearly since L and M are black, so L is white, K is black, implies by the conditions L plus K is black. Okay, and L plus K is black and M is white, implies M into L plus K is white, because the product of a black and a white is white. Next, M is white. Okay, so let's write it there only. So K is black, M is white, implies M into K is white, because product of a black and a white is white. Now we prove by contradiction. Suppose LM is black. Suppose LM, this arrow means is assigned black color. LM is black, then LM plus MK is equal to M into L plus K, and this is white, MK is white and LM is black. Contradiction, because black plus white should have been black. Okay, contradiction to the assumption, I mean the coloring. So therefore LM is assigned B is impossible. So therefore, LM must be assigned white, and we are done. So now we have a nice proof, right? We have proved that the product of two whites is white. A product of a white with a black is also white. So product of a white with anything is white. And once you get product of a white with anything is white, the proof is over here, right? Because in the given problem, we know here n was the smallest number where it was white originally. So n into anything is white. So this is white. And r is less than n. So since n is the smallest such number which is assigned white, all of these are black. So the remainder here is black as long as it's non-zero. So therefore, the black plus white is black. So capital N is black. So as long as a number is not divisible by n, it is assigned black. Okay. Now, if it is divisible by n, it must be assigned white because any multiple of n is white. Just now we have proved. So we are done. So this is the only way to color it. So the coloring scheme is the one given here. Pick any n, put all multiples of n as white, rest all black. That's the only coloring. Okay, is it clear? Okay. All right. So here is the last problem of the day. Okay. Last problem. So I really liked it actually. I think it was natural, at least to me. At least the flow of the argument was natural. Okay, all right. So let's try RMO 2018 problem, last problem of the day. I don't know if this has any, each vertex of a 5 cross 5 grid is either colored red or blue. Prove that there always exists 4 points which form the vertices of a square whose sides parallel to the outer sides and whose sides are parallel with sides parallel to the outer sides and have at least 3 points of the same color. Okay, so okay. By the way, I took this problem because the previous problem because it also has some kind of a sum and product black and white coloring. Okay, like if you call this product 1 minus 1 or something, I think there might be some, I don't know if it's possible, but it would be nice if there is again that assignment kind of a technique here. Somehow if you could put some variables x power I or something and play around with it and impose these conditions and get the answer using some kind of algebra, convert this problem to algebra by assigning labels like some very clever x power I, whatever, like something that Lauren did earlier, some roots of unity, some polynomial expressions, something. I think it can be done here. I get the feeling it can be done instead of doing this by hand like this. A cleaner proof or a more general thing can be achieved. Because for example, what if we colored not by just 2 colors but 3 colors and we came up with more general things? So I'm very interested if somebody could come up with that. Okay, right. Okay, so here is the RMO question. Prove that there always exists 4 points which form the vertices of a square with sides parallel to the outer sides and have at least 3 points of the same color. I think they are talking about these. Oh, square. Okay. So in other words, I should have drawn. It's not the grid in this problem, it's the squares. Okay, so it's like 4 cross 4 square Prove there exists 4 points which form the vertices of a square with sides parallel to the outer sides that have at least. But still on the, okay. Fine. I have to consider squares with the vertices on the. Two colors and a 5x5 grid, right? What does it remind you of? Two colors and a 5x5 grid. If you want to distribute 5 points among two colors, in my mind I'm like maybe some pigeonhole principle. I don't know if that's useful. I think we can do it with, we can actually, we can try it with. The dominoes here may not work, right? Okay, maybe it will actually, it depends how do you do it. Because this is about the vertices, right? Vertices are colored, it's a statement about vertices, so maybe this should not have been in a domino set. This is some other kind of a problem. Unless I can convert this to a dominoes problem. Can't we say, okay, I think this is pigeonhole, okay, looks pigeonhole to me. Like, if there are 5 points and they are colored by 2 colors, then definitely some 3 must be of the same color. Let's say those, whichever color it is blue. Blue. Oh, then we are done. I mean, if we put blue here, we are done. 3 vertices of the square have blue. So you cannot put blue there. Okay, if you put blue there, we are done. So we should put red here. I'll write it with blue. It's weird. I'll write here red, blue. Here also we are done. This will become a square. We can't put a blue here. If you put, we are done again. So this has to be a red. But at least some 3 must be of the same color. But all of them could be red actually. No contradiction. Here also, if you put red, I mean here also if you put blue, we are done. So we are forced. I think it keeps forcing things to be red, something like that. This also is red. But these two are red now. So this square, if there's one more red as other vertices, we are done. So they will force itself to be blue. I'm doing trial and error actually at this point. I should come up with some general argument. Some pigeonhole I have to do. Blue. So basically, if this condition is not possible, that means that any square has 2 blue and 2 reds, which will force a lot of things. Like this will become red and red because this square should have 2 blues and 2 reds. And this square has red and red here already, so this entire square, the remaining 2 must be blue and blue. Oh, done. Contradiction. You see, this one has 3 blue. Okay, this is not good. This is some trial and error. Should not run trial and error. Should run some pigeonhole. Some pigeonhole. Problem is that two simultaneous pigeonhole I cannot do. I mean, I cannot control. One of them could be blue, the other could be red. Okay. So Lauren notes that the total number of vertices is odd. That is true. But does that argument fly? Let's see. The problem is that certain vertices are common to multiple squares, no? You will be a little careful, but I think is it that simple? They're not coming exactly in pairs, right? I mean, if you take, okay, I want to apply it in each square maybe. So they're coming in pairs, meaning for a given square they're coming in pairs. Does that mean anything? So if you have blue, yeah, I think that, but it's in the right direction, I think. Maybe that's a good argument. Let's see. So what is the contradiction? So if you are going to assign blues and reds, what is the thing that you want to assign? Use the fact that it is odd. Do you want to count number of blues plus number of reds, total number of vertices that are assigned blue, number of vertices, number of vertices that are assigned blue plus number of vertices that are assigned red? That is 25, right? Which is 1 mod 2, whatever is odd. Now you want to count that in some other way. How many vertices are assigned blue? But you want to use the fact that given any square, it's there's 2 blues and 2 reds in it. Suppose. How do we count it? We can try to count. We can somehow come up with a way to break it up into parts and sum it up. Then this fellow will get counted in 2 squares. If you could count it in a disjoint way, it would have been nice, but we can't, no? That is the problem. If you count this, or rather if you count this, these 4 squares are done. Then if you count this, these 4 squares are done. And this is not counted, I know. Or we could try to overcount them and see what happens. This is not maybe a good idea. So I don't know how to implement Lorentz observation. B plus R is total number of thing is odd. I think more than overall odd parity, yeah, maybe it's odd parity is possible. Just have to come up with some other way to count it, which will give you even. How do we use that? For every square, maybe for every square we have to add some or all possible squares. Two cross two. It's very uneven, no? The boundary ones will not be counted, will be counted the least number of times. The inner ones will be counted most, it looks like. The vertices that are inside will get counted more. What is on the boundary will be counted less. So won't give me a full B plus R. Phi 2 cross 2 squares. Which phi? The central one and the outer 4. Okay. Still the central one will count it the most number of times, no? So it's not equal. So this one will get counted 4 times. And these guys will get counted only once. Okay, still I think if the parity is maintained, it's fine, I think. 4 times this is 4. Let's write the multiplicity on it. 4 times here, 1, 1, 1, 1, and 1. This one, 1, 1. But I guess this is not counted, no? Wait, in your count the outer squares, you miss certain squares, or you counted everything? Yeah, these points are missed. Yeah, that's not counted. Now I want to go back to my pigeonhole. I think it has to be done through pigeonhole only. Some pigeonhole. I think even if we do diagonal 5, even if we try with diagonal 5 may be better than trying to do 2 simultaneous ones. Even then, is it easy? It's not obvious. What if you have 3 blues? Again, you do trial and error. How many cases are there? 3 blues together, red, or just 3 blues together, we don't care about the remaining, or 2 blues and then 1 blue and in between a red, or red and a blue. Only 3 cases we have to do. We should do the 3 cases and finish it off. So what if you have blue, blue, blue? Then the other 2 must be red, other 2 must be red, other 2 must be red, and we are done, right? Oh no, other 2 must be, wait, is that correct? This must be red, sorry. This is blue, red, but anyway, this 3 will become red. I mean, this will become red because this should have 2 blue, 2 red. This will become red because this should have 2 blue, 2 red. And this will become red because this should have 2 blue, 2 red. So it will force 3 reds. I think it's just trial and error. Okay. Unless one of the cases fails and becomes interesting, I don't know. I don't have to erase it here. I think I should draw it again. The other case could be blue, blue, red, blue. Then what will happen? And this will become red, red. Then red, red, and red, red. Can we see a 3 red in a single box? No, not yet, I think. Maybe this blue red will force. Okay, that I can't tell actually. This is red, red. Okay, this will force blue, blue. Now it will force. We are done. Is it? Are we done? No, we are not done. Blue, blue. So red, red. Now we are done really. These three will become red. Right? So I think last case. Just maybe there's a nicer proof without trial and error actually. Some clever argument. Anyway, there are three cases, so it's okay. It's not a big deal. So, but I don't generally like cases, but if it is needed, we'll do it. So, blue. It's true, right? These are the only cases. Now again we start filling in what should be the blues. It says red. So 2 reds and 2 blues. Okay, I think I'm writing it all wrong. It should be here. I think this is, hopefully it will work. Let's see. This is the last case. Are we done? This is blue, red. Actually here red, red, blue, blue, right? Where square. This is red. And this is blue. Done again. I think this, it's working. I mean, you can in principle write a case by case boring looking proof. I wish there was. Okay. Alright, I mean, in principle it's done, but does anyone have a plan to attack this in some other way? I think it's some pigeonhole principle argument. You say some 3 blues must exist. Is it similar to that second problem? The third problem, 3 cross 1, the center one must be blue or something. Can we argue center one has to be blue? No, maybe not. 7 is not blue then. I mean, these 2 colors. Okay, anyway, I think we are done. So it's already around 2 hours. So let me just stop here, because the proof is anyway over. It's correct. One can finish off the proof by 3 cases. But if you know a simpler proof, please write it in the comments actually. If you come up with a shorter proof. And another thing which I would really love is if somebody comes up with a way to solve this problem by again assigning some powers of complex numbers or something like that to this problem, like more algebraic, any kind of an algebraic approach. If anybody could come up with for this problem, it will be awesome. Okay, but I don't know if there exists one, but it looks very, very algebraic to me. Some generating function, something, I don't know. Okay, all right. So see you all. Maybe next Saturday or Tuesday, it depends. And I want to do more combi problems. I think the kind of problems that we have not yet done, this is coloring and dominoes. What others? Maybe some graph theory or linearity of expectation. Okay. So let's see, maybe graph theory. Some basics of graph theory might have come in, I know that it has come in RMO, it has come in INMO for sure. So I'll look at the old RMO papers and decide. So if you want to practice, make sure you try old RMO papers and try British Math Olympiad papers. Okay. All right. See you all. Bye.